How long would a human body really last on every planet in the solar system? Not in science fiction, not with super technology, just under the real conditions of each world, from the freezing darkness beyond Neptune to the crushing heat of Venus. Each planet ends human survival in its own silent way. Some would kill in seconds. One might seem survivable for a moment. Only one truly lets life breathe. Before the journey begins, take a moment to like the video, subscribe to the channel, and settle in for a calm descent through the deadliest worlds around the Sun. Far beyond Neptune, the solar system becomes quiet in a way that is difficult to compare with any place near Earth. The Sun is still there, but it no longer rules the sky with warmth or brightness. It appears as an intense star, sharp and white against a black background, yet its power has faded across the immense distance. In this remote region, the space between objects is vast, almost beyond ordinary thought. Small icy bodies travel along slow paths, dust is sparse, light is thin, heat is almost absent. The scene holds very little that can support a human body, and very little that can even slow its decline. A person placed here without protection does not first die from cold in the simple everyday sense. The cold is severe, but empty space carries heat poorly because there is almost no matter there to touch the body and remove warmth. The more immediate danger is exposure itself. The body's made for pressure, for air, for the steady presence of surrounding gas pressing gently against skin and lungs. In this distant outer region, there is essentially none. The body meets vacuum, or something very close to it, and vacuum is not a breathable emptiness. It is an absence of the basic condition that human life depends on from moment to moment. The first need is oxygen, not as a concept, but as a continuous physical supply. Blood carries oxygen to the brain, and the brain depends on it without pause. In this outer region, with no usable atmosphere, breathing cannot continue. If a person arrives unprotected and tries to inhale, nothing enters the lungs that can sustain life. Consciousness begins to fade quickly, not because the setting is dramatic, but because the body simply runs through the oxygen already present in the blood. Within a short span, measured in seconds rather than minutes, clear thought weakens, coordination goes, awareness narrows. Soon it is lost. Pressure matters at the same time. Human tissues are mostly water, and water behaves differently when surrounding pressure falls too low. It does not mean that a person explodes, because the skin and other tissues still hold the body together. What happens is quieter and more dangerous. Moist surfaces begin to swell. Fluids near the skin and in soft tissues respond to the low pressure. The body starts to bloat. Saliva and moisture in the mouth can begin to boil, not because they are hot, but because the pressure around them has dropped below the point where a liquid remains stable. This is one of the strange truths of space exposure. Boiling, in this case, belongs to pressure, not to flame. The lungs are especially vulnerable. If the breath is held, expanding gas can injure delicate tissue. The body survives vacuum exposure slightly better when air is allowed to leave rather than being trapped. Even then, survival without rapid rescue remains brief. The problem is not a single dramatic injury. It is a cluster of failures arriving together. Lack of oxygen begins at once. Pressure no longer supports normal function. The circulation struggles. The brain receives less of what it needs. The body's not built to continue under those conditions. The cold remains part of the setting, but it works in a slower and more subtle way than fiction often suggests. In deep space beyond Neptune, the background environment is only a few degrees above absolute zero, and sunlight at that distance is reduced to a small fraction of what Earth receives. A human body does radiate heat away, and over time it would cool. Yet this does not happen instantly. In empty space there is no cold wind, no cold water, no dense gas to draw heat out quickly. The body loses heat by radiation, a slower process. So in this outer region, if a person is exposed directly, the first decisive limit is lack of air and pressure, not freezing solid in an instant. The cold waits behind the faster failures. Radiation is present as well, though it is not the main cause of immediate death in a sudden exposure. The outer solar system still lies within the broad influence of the Sun, yet it is also a place where high-energy particles from deep space matter more. Over long periods, radiation becomes a serious danger to living tissue. It damages cells, raises cancer risk, and threatens organs and the nervous system. But in the first moments of unprotected survival, radiation is not what ends life. It belongs more to long journeys and long habitation than to the first minute of exposure. The weakness of sunlight changes the appearance of everything. Surfaces of distant icy bodies reflect a pale, limited light. Shadows remain black and hard-edged. The darkness between objects feels complete because there is so little scattered brightness. On Earth, air softens light and spreads it gently. Here, there is no such veil. Illumination falls directly and harshly where it reaches, then stops. Human sight would still function if the eyes were protected, but the scene would feel stark and stripped down to essentials. There is no weather here in the ordinary sense, no blue sky, no moving cloud deck, no sound moving through air. Only silence and thin light over ancient ice and stone. If the person has a suit, survival changes completely, because the suit becomes an artificial world. It supplies pressure, oxygen, temperature control, and shielding from part of the radiation environment. Without that barrier, the body is exposed to a place that does not negotiate. Human life in the outer solar system depends entirely on carried conditions, not native ones. The environment gives nothing freely. It offers no breathable gas, no liquid water, no warmth that can be used by the body without elaborate help. Even standing on a solid icy surface would not make the place more hospitable. Ground alone is not safety. A human being needs an envelope of Earth-like conditions carried around the body at all times. So the answer in this first and farthest region is simple in principle. Even if the details are complex, a person without protection lasts only a very short time. Useful consciousness survives for seconds. Biological survival may continue a little longer, but not by much unless rescue and repressurization come immediately. Beyond Neptune, distance itself shapes the truth. The body enters a realm where sunlight is faint, matter is sparse, and the basic pressure of life is gone. In such a place, survival is not measured by endurance against scenery. It is measured by how long the body can resist the absence of air, and that is only a brief interval before the outer darkness becomes final. In the realm of dwarf ice beyond the major planets, the solar system appears less like a set of grand worlds and more like a scattered archive of frozen remnants. Pluto is the best known of these distant bodies, but it is only one among many objects that circle in the far cold, where sunlight arrives weak and thin, and every surface seems held in a long, slow pause. Here the ground is real in a way that open space is not. There are plains, ridges, impact scars, and layers of frost. Yet for a human body, this change from vacuum to surface does not mean safety. It only changes the manner of danger. The body now has a place to stand, but almost nothing else it needs. Pluto offers a useful example because it has been observed closely enough to reveal a world of nitrogen ice water ice as hard as rock, methane frost, and a surface shaped by ancient and ongoing processes. Its atmosphere is extremely thin, made mostly of nitrogen, with traces of methane and carbon monoxide. Thin means far thinner than the air at the top of Earth's highest mountains. It is not an atmosphere that can be breathed, and it does not provide meaningful pressure for human survival. It drifts and changes with Pluto's long seasons and distance from the Sun, sometimes expanding slightly as surface ice is warm and sublime, then collapsing again as the world cools. Observations indicate that this atmosphere exists, but it remains tenuous enough that an exposed human body would still face conditions close to vacuum. The first experience on such a surface would not be wind or weather in the familiar sense. It would be the strange stillness of a horizon under a black sky, with the sun appearing as a brilliant point rather than a warming disk. The light would be dim, but not absent. It would cast long shadows across pale ice and darker red-brown terrain, revealing textures that look firm and silent. The cold would be profound. Pluto's surface temperatures are commonly measured in tens of degrees above absolute zero. In ordinary language, this means cold so extreme that familiar materials behave differently. Water is not a flowing substance here. It forms a rigid framework. Nitrogen and methane can freeze into part of the landscape. Yet even here, the body does not die first from becoming an instant block of ice. Again, the first crisis is pressure and air. An exposed person on Pluto could not breathe the atmosphere in any useful way. There's almost no oxygen, and the total pressure is so low that the lungs cannot work normally. Consciousness would fade rapidly for the same reason it fades in open space. Oxygen already present in the blood would be used up within seconds. The body would begin to swell from low pressure. Moist surfaces would react. Blood circulation would continue briefly, but with less and less value to the brain. The presence of a thin atmosphere does not rescue the body from vacuum-like exposure, because that atmosphere is too insubstantial to do the job Earth's air performs continuously. The surface itself introduces another form of contact with the environment. If bare skin touched Pluto's ground, the cold material would draw heat away faster than empty space does, because now there is direct contact. Ice and frozen soil at such temperatures would injure tissue almost immediately. Skin would freeze, become brittle, and suffer severe damage in moments. Any part of the body exposed through torn clothing or suit failure would begin to lose function quickly. This is a more direct cold than the cold of empty space, yet it still joins rather than replaces the main crisis. A person would likely lose consciousness from lack of oxygen before the full long effect of freezing spread through the whole body. The thin atmosphere also means there is little protection from radiation and little moderation of temperature between sunlight and shadow. On a world like Pluto, sunlight is weak, but shadow remains deeply cold. There is no thick layer of air to move heat around, no dense blanket to smooth the difference between one place and another. The body on the surface is therefore exposed to a setting that combines hard cold, direct radiation, and almost no pressure. A suit is not simply helpful here. It is the difference between a survivable expedition and death within a brief span. Other dwarf worlds and icy bodies in this outer region follow the same broad rule, though each has its own details. Eris is even farther away on average and colder still. Makemake appears to have little or no lasting atmosphere under most conditions. Haumea spins rapidly and stretches into an unusual shape, but its surface remains a frozen vacuum environment. Triton, although classified as a moon rather than a dwarf planet, shares many of the same outer conditions and has an extremely thin nitrogen atmosphere above frozen ground. In all these places, The scenery changes from one body to another, but the human result changes very little. There is no breathable air, no useful pressure, and almost no native warmth. Survival without protection remains measured in seconds of awareness, and perhaps a minute or two before biological death becomes irreversible. There is also the question of gravity. Pluto's gravity is much weaker than Earth's, only a small fraction of what the human body is built around. In the first moments of exposure, this matters less than air and pressure, but it changes how the body would move. A person in a working suit could take long, slow steps and rise easily from the ground. Loose particles would fall gently. The whole environment would feel lighter, less anchored. Without a suit, though, that strange grace would offer nothing. Biology does not become more tolerant of vacuum because gravity is weak. The body still needs the same internal chemistry, the same oxygen supply, the same pressure range that it needs anywhere else. So the survival answer on Pluto and similar outer icy worlds is severe but calm in its logic. Ground is present, but it does not provide life. Atmosphere is present in some cases, but it does not support breathing. Sunlight reaches the surface, but it does not warm it into habitability. The outer dwarf planets are not empty like open space, yet they remain just as lethal to an unprotected human body. A person lasts only a short time, with useful consciousness measured in seconds and death following soon after unless rescue is immediate. In this realm of dwarf ice, survival fails not because the landscape is violent, but because it is too cold, too thin, and too far removed from the conditions that living tissue requires. Neptune's upper sky is not a place with the surface waiting below a layer of weather. It is a deep atmosphere spread over a hidden interior, and the visible world is made of cloud tops, hazes, and moving bands of gas. From far away it appears calm and richly blue, one of the most beautiful planets in the solar system. Up close, that beauty belongs to a place of cold, wind, and pressure, a place where a human body cannot remain alive without complete protection. Here the question of survival changes slightly from the icy dwarf worlds. There is no firm frozen ground to stand on. There is only descent into gas, beginning in the highest regions where the atmosphere is most rarefied and moving inward toward greater density. In the upper atmosphere, the light from the distant sun is weak, yet Neptune still reflects enough of it to create a luminous blue globe. The colour comes mainly from methane in the atmosphere, which absorbs red light and leaves more blue light to scatter outward. The air is made mostly of hydrogen and helium, with methane mixed in at lower levels. None of this is breathable. There is no oxygen reserve waiting in the clouds, no pressure range naturally suited to human lungs, and no stable zone where an exposed person could simply float and survive for long. The body entering Neptune's outer sky would still meet an environment hostile from the first second. At the highest levels, the atmosphere is thin compared with deeper layers, but it is not helpful thinness. It does not become a gentle substitute for Earth's air. It remains chemically useless for breathing and physically dangerous because pressure changes rapidly with descent. A person without a suit in this region would first suffer from oxygen deprivation, just as in open space or on Pluto. Even if some gas surrounded the body, it would not sustain the lungs. Consciousness would fade quickly. The body would not have time to adjust. Human physiology does not gradually learn an alien atmosphere in the moment of crisis. It simply begins to fail when oxygen is absent and pressure falls outside the narrow range it can tolerate. Neptune adds another danger early in the descent motion. The planet is famous for extremely strong winds. Some of the fastest winds measured anywhere in the solar system move through its atmosphere, reaching speeds greater than the speed of sound in Earth's air. The exact wind pattern varies with altitude and season, and observations indicate a complicated structure of jets, storms, and shifting cloud systems. In practical terms, this means that even a protected craft or probe must endure a restless environment. For an unprotected human body, such motion would not merely feel forceful. It would be part of a chaotic descent through cold gas that offers no control, no stable footing, and no breathable refuge. The cold in Neptune's upper atmosphere is intense. The planet receives very little solar energy because of its great distance from the Sun. Temperatures in the upper cloud regions fall to values far below anything naturally experienced on Earth's surface. Touch, if it could be felt in an exposed state for more than a moment, would bring severe freezing injury. Yet again, cold is not necessarily the first final cause. The faster failure remains lack of oxygen and the mismatch between the body and its surroundings. A human being does not need to cool all the way to Neptune's ambient temperature for life to end. The body only needs to lose access to pressure balance and breathable air for the process to begin almost at once. As descent continues, the atmosphere grows denser. This might sound at first like an improvement, because dense gas seems closer to the idea of air. In reality, it means the body moves from one lethal condition into another. Pressure rises, and rising pressure in a hydrogen-helium atmosphere does not become human-safe on the way down. There is no broad middle layer where a person could breathe or stand. Instead, the body would pass through regions where gas resistance increases, temperature begins to change, and the surrounding pressure soon exceeds what unprotected tissues can withstand. If consciousness somehow remained, which is highly unlikely after the initial exposure, the person would be descending into a more crushing environment rather than a more hospitable one. This descent also lacks a natural endpoint that human intuition prefers. On Earth, falling through air leads to land or water. On Neptune, deeper layers lead to denser and denser material, to immense pressures and temperatures, and to forms of matter that are not part of ordinary experience. Planetary scientists model a transition from the upper atmosphere into deep layers rich in volatile substances such as water, ammonia, and methane under exotic conditions. Then farther inward toward a hot, dense interior. It remains uncertain in detail how sharply one layer changes into another, but the broad picture is clear. Neptune is not a place where a human falls through weather and arrives at a normal ground. It is a place where descent becomes burial in atmosphere and then in extreme planetary depth. The sky itself would also change during this inward movement. At first, there may be some dim scattered light from above, filtered through high haze and cloud structures. Deeper down, visibility would fade. Clouds of methane ice and other condensates would obscure distant sight. Light from the sun, already weak at Neptune's distance, would be absorbed and scattered away. The world would become increasingly enclosed, not by walls, but by thickening gas and darkness. For a person, the emotional image might seem quiet, but the physical reality would be immediate and unforgiving. So survival on Neptune's upper sky is brief, not because one single dramatic event occurs, but because every aspect of the environment rejects human life at once. The air cannot be breathed. The pressure is wrong from the start and becomes worse with depth. The cold is severe. The winds are violent. There is no solid surface to orient the body, and no habitable layer known to exist in the visible atmosphere. A person exposed there would remain conscious only for seconds, then die soon after from oxygen deprivation and environmental stress long before deeper pressure and heat could complete the destruction. Neptune's blue calm is therefore only an appearance from a distance. In the upper sky itself, survival is measured by the very short time it takes the body to fail in an atmosphere that is broad, beautiful, and entirely unfit for human life. Uranus appears gentler than Neptune when viewed from afar. Its colour is paler, its visible atmosphere often seems quieter, and its place in the solar system gives it an impression of stillness rather than force. Yet this impression belongs only to distance. Uranus is not mild in any human sense. It is an immense world of gas and fluid layers, with no ordinary surface and no natural region where a human body can remain exposed and alive. Its upper atmosphere begins in cold sunlight and thin haze, then deepens into a broad envelope of hydrogen, helium, and methane. The planet does not offer any stable transition from danger into safety. It offers only one fatal environment after another, arranged by depth. From the outermost visible levels, Uranus receives very little warmth from the Sun. The sunlight that reaches it is faint compared with the light Earth receives, and its pale blue-green colour comes mainly from methane, absorbing red wavelengths and leaving more blue and green light behind. What looks serene from a telescope is in fact a place of severe cold. The upper atmosphere reaches temperatures low enough to rank among the coldest found on any planet in the solar system. For the human body, this means that the environment begins from a baseline far outside the range life can tolerate. Still, as in the outer regions already described, cold alone is not the first limit. The first limit remains the absence of breathable air and Earth-like pressure. A person exposed in Uranus's upper atmosphere would not find oxygen waiting in the surrounding gas. Hydrogen and helium dominate the air, with methane present in smaller amounts. None of these gases can support human respiration. Breathing would immediately fail as a life-sustaining act. The lungs require oxygen delivered at suitable pressure. Here there is neither. Consciousness would therefore fade quickly, in a span measured in seconds, because the brain consumes its limited oxygen supply without replacement. This pattern remains one of the most consistent truths across the solar system. Whether a body is surrounded by vacuum or alien gas, survival depends first on whether oxygen can be delivered to living tissue. On Uranus, it cannot. The body also depends on external pressure remaining within a narrow and familiar range. In the high atmosphere of Uranus, pressure may begin low in the outer levels, then increase steadily as descent continues. This does not create a comfortable layer along the way. Instead, it creates a gradient of worsening mismatch. If the pressure is too low, tissues swell and exposed moisture behaves abnormally, much as it does in near-vacuum environments. If the pressure becomes too high, the body is compressed, and its internal systems are stressed beyond what natural adaptation can handle. Human survival equipment can manage controlled pressure differences for a time, but an unprotected body has no such system. It is simply placed into a planetary atmosphere built from the wrong gases under the wrong conditions. The stillness often associated with Uranus also needs careful understanding. The planet can appear visually bland in ordinary images, without the dramatic storm scars seen on Jupiter or the dark storms once observed on Neptune. Yet Uranus is not an inactive sphere. Observations have shown cloud structures, seasonal changes, bands of motion, and episodes of storm activity. Its atmosphere is dynamic even if its motions are less obvious at first glance. For a human body, however, the distinction between quiet-looking and active-looking weather has little practical value. Even a perfectly calm hydrogen-helium atmosphere would still be deadly without oxygen or suitable pressure. If winds are present, they only add motion and instability to an already unsurvivable descent. As a person sinks deeper, the gas thickens. What begins as exposure to a cold alien sky becomes immersion in an atmosphere with increasing density and pressure. There is no solid crust just below the clouds. Uranus belongs to the class often called ice giants, though that phrase can mislead if understood too literally. It does not mean a shell of ordinary ice near the top. It refers instead to the larger role of substances such as water, ammonia, and methane in the deep interior compared with Jupiter and Saturn. Under the enormous pressures inside Uranus, these materials do not behave like familiar ice in a freezer or water in a stream. They exist in exotic states shaped by pressure and heat. A human body does not approach these depths as an explorer approaches land. It approaches them as matter, sinking into a planetary interior. Temperature also changes with depth in ways that matter greatly. The upper atmosphere is extremely cold, but deeper regions become warmer as pressure rises and energy is stored below. This means Uranus combines opposite dangers along the same vertical path. Near the top, cold and low pressure dominate. Farther in, crushing pressure and increasing heat take over. There is no human-safe band known between them, no suspended platform of habitability. Even if a person could somehow remain conscious beyond the first seconds, which is not realistic, descent would move from one lethal mode to another. The environment does not level out into something manageable. It grows steadily more extreme. Light fades during this inward movement. The faint sunlight available at Uranus is already limited, and cloud layers scatter and absorb it further. At higher levels, pale illumination may still reveal haze and broad atmospheric tone. Deeper down, the scene becomes dim and enclosed. Vision would narrow as gas thickens and suspended particles interfere with long sight. There would be no horizon in the terrestrial sense, no landform to guide orientation, only a gradual loss of external reference as the planet closes in through atmosphere alone. The human sense of up and down, already challenged by weak visual cues, would matter less and less as the body lost control and consciousness. Gravity on Uranus is not the main killer in this situation, yet it shapes the descent. The body is drawn inward while the atmosphere thickens around it. Without wings, engines, or a protective craft, there is no meaningful way to resist this movement. Falling here is not a brief event. It is a transition from one atmospheric regime into another, driven by gravity and structured by pressure. Human survival time remains short not because the whole descent finishes quickly, but because the body fails very early in the process. So Uranus, despite its pale appearance and apparent quiet, gives no refuge to an exposed human being. Its upper atmosphere is far too cold. Its gases cannot be breathed. Its pressure profile moves only from one harmful condition toward another, and its deeper regions become progressively more hostile. A person without protection would lose useful consciousness within seconds from oxygen deprivation, and would die soon after, long before the deeper layers of the planet could be reached. The stillness of Uranus is therefore only visual. In physical terms, it's a calm-looking world that remains completely closed to unprotected human life. Saturn's outer haze seems softer than the skies of the more distant giants. Its colours are muted gold and pale brown. Its rings cast broad shadows across the atmosphere, and from afar the whole planet appears less severe than Jupiter and less remote than Uranus or Neptune. Yet the softness is visual only. Saturn is a gas giant, and its outer layers offer no solid surface, no breathable air, and no natural shelter for a human body. The region begins in thin upper atmosphere and haze, where sunlight still reaches the cloud tops in weakened form, then deepens steadily into denser gas. In this upper zone, survival depends entirely on artificial protection. Without it, the body fails quickly for the same central reason that applies across nearly all hostile worlds. The environment does not provide the pressure and oxygen that human life requires. The outer atmosphere of Saturn is made mainly of hydrogen and helium, with traces of other substances that help shape the visible clouds and colours. Ammonia plays an important role in the upper cloud decks, and deeper levels contain ammonium hydrosulfide and water clouds under different pressure and temperature conditions. These layers create the banded appearance seen from telescopes and spacecraft, though the colours are often subtle and partly hidden by high haze. To a human observer descending into this region, the first impression might be one of broad, luminous calm, with light filtered through diffuse gold and cream tones. But this calm does not make the place safer. The gases cannot be breathed. The body has no use for a sky made of hydrogen and helium, however beautiful it may look. At the highest levels, the pressure may still be too low for normal human survival, even before considering the lack of oxygen. In such a region, an exposed body would begin to suffer from oxygen deprivation almost at once. Consciousness would narrow and then disappear within seconds, because the brain cannot continue without constant oxygen delivery. The presence of surrounding gas does not change that fact when the gas contains nothing the lungs can use. Human breathing is not simply movement of air in and out. It is the exchange of oxygen and carbon dioxide across delicate tissue under suitable pressure. Saturn's outer haze provides neither the right chemistry nor the right physical support. The body also depends on temperature staying within a narrow living range, and Saturn's upper atmosphere is cold enough to threaten exposed tissues immediately. The distance from the Sun means that solar heating is far weaker than at Earth. The topmost visible layers are frigid, though not in a simple uniform way. Sunlight, shadow, altitude, and atmospheric motion all shape local conditions. Still, from the point of view of an unprotected person, the exact temperature pattern matters less than the broad reality that the environment is deeply cold and inhospitable. Bare skin would freeze quickly. Moisture would behave abnormally under low pressure. The body would not endure long enough for the full long process of whole body freezing to become the defining cause. It would lose consciousness first from lack of oxygen, and then continue rapidly toward death. Saturn also introduces the problem of sinking. Unlike a rocky planet or icy dwarf world, it does not offer a firm horizon that can be reached and used as a reference point. The visible cloud tops are not a surface in the ordinary sense. They are the upper layers of a deep atmosphere. A person entering without support would descend into gas rather than land. At first this might seem gentle, because gas can slow falling more than open vacuum can. But gentleness is misleading here. The descent means the body is being carried from one bad condition into another. Pressure rises steadily, density increases, the atmosphere thickens. There is no broad layer where the gases suddenly become suitable for human life. There is only a progression from too little pressure and no oxygen toward greater pressure and still no oxygen. The ring shadows add a striking visual element to this region. Saturn's rings are thin compared with the planet's size, but they spread so widely that they can cast long, dark bands across the upper atmosphere. In those shadowed areas, incoming sunlight is reduced even further. The result is a sky that can vary in brightness across enormous distances, with hazy light in one region and dimmer muted tones in another. This has value for appearance, not for survival. The shadow does not bring relief. It only reshapes an already cold and alien light. The body exposed there still faces the same unchanging reality. There is no air to breathe, no stable pressure to preserve normal function, and no dry solid ground on which to wait for rescue. Wind also matters in Saturn's outer atmosphere. Though Saturn can look smoother than Jupiter, its atmosphere is active, with powerful zonal winds moving around the planet. Near the equator, these winds can become extremely fast. Cloud bands drift, shear, and change with time. Storms can develop, including rare but very large disturbances. For an unprotected person, such motion would not be something to observe for long. It would be part of a disorienting fall through cold gas, with changing force and no meaningful control. Even with perfect calm, the environment would still be unsurvivable. With strong atmospheric motion, it becomes even less stable. As descent continues, the body would move into layers where pressure begins to exceed what human tissues can tolerate. The problem shifts from one edge of survivability to the other. At the top, there is too little useful pressure and no oxygen. Deeper down, there is too much pressure, still no oxygen, and increasing thermal energy. Saturn does not contain a middle human zone known to science, where a person could float naturally and live without a suit. Beneath the clouds, the hydrogen atmosphere thickens into fluid states with no sharp boundary that can be called a normal surface. For the body, that means there is no natural stopping place, only deepening immersion in planetary material. So the answer in Saturn's outer haze remains severe and simple. An exposed human lasts only a very short time. Useful consciousness is measured in seconds because oxygen is absent. Death follows soon after, unless complete pressurized rescue occurs almost immediately. Cold, wind, and descent all shape the setting, but they do not replace the main truth. Saturn's upper atmosphere is a broad, beautiful layer of haze and cloud built from the wrong gases under the wrong pressures. It may look soft under ring-shadowed light, yet it offers the human body nothing it can use. Survival there is brief because the outer haze is not an airy sky above a world. It is the beginning of the world itself, and it begins in a form that life from Earth cannot endure. Jupiter's high atmosphere appears more dramatic than Saturn's from the first glance. The planet is crossed by dark belts and bright zones, immense storms turn through layered clouds, and the great red spot endures as a vast rotating system larger than Earth itself. Yet this visible grandeur belongs only to the uppermost accessible view. Jupiter is not a world with weather above a solid landscape. It is a deep planetary atmosphere descending into increasing density, pressure, and heat. In its highest layers, a human body meets cold gas, powerful motion, and a chemical environment that cannot support life. Survival begins and ends with the same fundamental limit found throughout the outer solar system. The body depends on oxygen and suitable pressure, and Jupiter provides neither. The upper atmosphere is composed mainly of hydrogen and helium, with smaller amounts of methane, ammonia, water vapor, and other trace compounds that help produce the cloud layers and colors seen from afar. The uppermost visible clouds are largely ammonia ice, with deeper cloud decks thought to include ammonium hydrosulfide and water, under warmer and more compressed conditions. These substances form part of a broad and active weather system, unlike anything on Earth in scale. Still, for an exposed human, the chemistry has a simpler meaning. None of these gases can be breathed, even where atmosphere is present. The lungs cannot draw life from it. A person entering Jupiter's high atmosphere without protection would begin to lose consciousness within seconds as oxygen already carried in, the blood is consumed and not replaced. Jupiter's atmosphere adds another major danger of very early radiation. The planet possesses an enormous magnetic field, and this field traps charged particles in belts of intense radiation around the planet. Near Jupiter, radiation levels can become severe enough to damage electronics and threaten spacecraft systems. For a human body, prolonged exposure to this environment would be deeply harmful. In the immediate first moments of direct exposure, lack of breathable air remains the fastest limit, but Jupiter's radiation makes the region even less forgiving than the upper atmospheres of the other giant planets. A person near Jupiter without shielding is not only suffocating in alien gas, the body is also entering one of the harshest radiation environments in the solar system, outside the immediate vicinity of the Sun. The visible atmosphere is cold at the cloud tops, but it is not still. Jupiter's belts and zones are shaped by strong east-west winds that move at high speed around the planet. These winds interact, shear past one another, and feed storms that can persist for years or even centuries. The Great Red Spot itself is a deep anticyclonic storm, and many smaller vortices and convective systems mark the atmosphere across different latitudes. In the high atmosphere, a human body would have no control over such motion. Even if there were some temporary level at which descent slowed, the body would be carried by turbulent flow through a region of extreme instability. Motion, cold, and lack of oxygen would combine at once, leaving no room for prolonged survival. At first, the pressure in the very highest levels may be too low for the body's normal function, especially without any oxygen present. As descent continues, pressure rises steadily. This does not improve survivability. It simply moves the body from one fatal condition toward another. Low pressure near the outermost region threatens swelling of tissues and abnormal behavior of exposed moisture. Greater pressure below begins to compress the body and change the behavior of gases in and around it. Human physiology tolerates only a narrow pressure range without special support. Jupiter offers no such supportive band for an unprotected person. It offers only a vertical path from cold, thin gas into thicker, hotter, more crushing layers. Light in Jupiter's upper atmosphere has a different quality from the dim blue or pale green worlds farther out. Jupiter still receives much more sunlight than Uranus or Neptune, though far less than Earth. The clouds are therefore more visibly structured, with bright high regions and darker lower belts, shadows cast by towering formations, and local colour from chemistry and depth. Yet even here the human experience would not linger on beauty for long. The body would be overwhelmed very quickly by the absence of oxygen. Vision might register broad amber, white, and brown expanses, perhaps the curve of a nearby cloud bank or a dark opening into deeper layers. But awareness would fade before those impressions could settle into anything lasting. There is no solid ground waiting beneath the clouds. This remains one of the most important truths about Jupiter. The planet's atmosphere passes into increasingly dense fluid states, and deeper still, hydrogen may enter forms unlike anything found at Earth's surface, including metallic hydrogen under enormous pressure. The exact details of the transitions depend on models and measurements, and some internal boundaries remain scientifically uncertain in fine structure, but the broad pattern is clear. Jupiter does not allow a human body to descend through weather and arrive on a surface. It allows only continued inward movement into regions that become more compressed, hotter, darker, and more physically destructive. Temperature also rises with depth after the cold cloud-top region. This means Jupiter contains both freezing upper conditions and deeper layers of extreme heat. For a human body, this creates a progression with no safe interval. At first, there is cold, alien gas, low useful pressure, and no oxygen. Then come higher pressures, thickening atmosphere and increasing thermal stress. The body would die long before reaching the depths where heat becomes one of the dominant destructive forces. Even so, the structure of the planet matters because it shows that Jupiter is not merely a cold sky. It is a deep engine of pressure and energy, and the visible atmosphere is only the beginning. Gravity on Jupiter is stronger than Earth's at the cloud top level, though not so overwhelming that it alone defines the first seconds of survival. What it does ensure is steady inward pull through the atmosphere. The body cannot remain suspended naturally in any meaningful way. Without a craft, balloon, or other support system, descent continues while the atmosphere changes around it. Human survival time therefore remains short, not because the planet instantly crushes the body at the very top, but because the body fails very early from more immediate biological limits. Suffocation comes first. Radiation adds threat. Pressure and heat grow worse below. So Jupiter's high atmosphere, for all its splendor, gives almost no time at all to an exposed person. Useful consciousness lasts only seconds because there is no breathable oxygen. Death follows soon after unless complete rescue with pressure and life support occurs almost immediately. Radiation makes the region especially hostile. Winds and storms remove any sense of stability. Pressure changes steadily with depth, and no solid surface lies beneath the cloud tops to offer rest or refuge. Jupiter appears rich with motion and colour, yet from the human biological point of view, it is as closed as deep space. Its high atmosphere is not a place to endure. It is the upper threshold of a giant world where the body fails almost at once, and the deeper violence of the planet remains far below, unreachable by the living. Between the giant planets and Mars, the solar system opens again into a broad middle distance that seems, at first glance, less hostile than the atmospheres of Jupiter or Saturn. There are no crushing cloud decks here, no immediate descent into pressure, no racing bands of hydrogen and helium. Instead, there is open space, sunlight somewhat stronger than in the outer reaches, and long empty intervals between one world and the next. Yet this region remains deadly in the same direct way that all unprotected space is deadly. The absence of atmosphere, the absence of pressure, and the long exposure to radiation make survival extremely brief. The setting changes from giant planet sky to open interplanetary void, but the human body still faces an environment that offers none of the basic conditions it needs to continue. Here the sun no longer appears as the diminished star seen beyond Neptune. It grows brighter as the distance inward decreases, though it is still much weaker than it is near Earth. The light falls more clearly across spacecraft hulls, rocky fragments, and the distant faces of moons and asteroids. Shadows remain sharp because there is no air to soften them. The darkness between sunlit objects is deep and absolute. There is still no sound moving from place to place, no wind in the terrestrial sense, and no atmosphere through which a human voice or breath could travel. The scene is not violent in appearance. It is calm, open, and silent. But this calm remains entirely indifferent to living tissue. A person exposed in this middle interplanetary region without a suit would encounter vacuum almost immediately, just as in the far outer solar system. The lungs would have no usable air to draw in. Oxygen already carried in the bloodstream would begin to run out within seconds. Conscious thought would narrow, then disappear. The brain, which depends continuously on oxygen, does not remain functional for long once that supply is interrupted. This remains the first decisive limit. Survival is not lost because of distance from help in an abstract sense. It is lost because the body cannot maintain its most basic exchange with the environment when the environment contains almost nothing. Pressure again is central. Human life at the surface of Earth depends on being surrounded by gas pressing gently against the body, especially across the delicate internal surfaces of the lungs. In open space between the planets, that condition vanishes. The body does not explode, but it does begin to swell as low pressure allows dissolved gases and exposed moisture to behave abnormally. Saliva and moisture in the mouth can begin to boil at normal body temperature because the surrounding pressure has dropped so far. Skin and internal tissue still hold the body together, but the normal balance is lost. This is not a dramatic tearing apart. It is a failure of support, a removal of the external physical framework within which the body is designed to work. Temperature in this region depends strongly on sunlight, shadow, and heat exchange with nearby objects. This means the experience of cold or heat is less simple than it seems. In shadow, surfaces can become extremely cold. In direct sunlight, exposed material can heat intensely because there is no atmosphere to spread energy or carry it away by moving air. A human body in a suit must manage both extremes at once. Without a suit, however, the body does not live long enough for ordinary ideas of freezing or overheating to fully define the outcome. The immediate cause remains lack of oxygen and pressure. Even so, the middle interplanetary region introduces a slightly stronger solar presence than the outermost dark. The sun begins to matter more here, not as a source of comfort, but as a source of radiant energy that creates sharp contrast between blazing light and deep shadow. Radiation is one of the major long-term hazards of this part of the solar system. Outside Earth's atmosphere and magnetic protection, the body is exposed to solar radiation and to high-energy particles coming from beyond the solar system. Solar storms can sharply increase this danger, sending charged particles through space in ways that threaten both astronauts and electronics. Over long journeys, radiation damages cells, harms blood-forming tissue, raises cancer risk, and affects the nervous system and other organs. It is not usually the fastest killer in sudden exposure, but it shapes the reality of travel through this region. Even with air and pressure supplied by a spacecraft or suit, the middle distance between the giant planets and Mars remains a biologically difficult corridor because of radiation alone. Microgravity also defines the environment, though it is not lethal in the first minutes. Far from a planet or moon, a body floats freely, no longer anchored by familiar weight. Over time this changes muscles, bones, circulation, and balance. Fluids shift upward in the body. Muscles weaken when they no longer work against gravity. Bones lose mineral content. These are slow changes, meaningful for missions and habitation, not for sudden direct exposure. Yet they belong to the region because they show that even protected survival here is never natural in the earthly sense. A spacecraft can provide air, water, temperature control, and some radiation shielding, but it cannot make open space biologically ordinary. It can only create a temporary local substitute. This middle distance also contains debris, though far less than popular imagination often suggests. Asteroids are not packed closely together. Spacecraft do not usually weave constantly through nearby tumbling rocks. Most of this region is empty on scales that overwhelm ordinary intuition. That emptiness matters because it means rescue is difficult not simply by danger, but by geometry. Distances are large, travel times are long, and nearby help may not exist at all. Yet once again, this practical isolation is not the first cause of death for an exposed person. The body loses useful consciousness in seconds long before the distance to rescue becomes the main story. With a suit, survival can extend from moments to hours, depending on life support and system condition. With a spacecraft, survival can extend far longer, but those conditions are artificial islands carried through vacuum. The region itself contributes nothing breathable, nothing drinkable, nothing warm enough and stable enough for the human body to use directly. Interplanetary space between the giant planets and Mars is therefore a place where technology, not environment, keeps life going. Remove the technology, and the underlying truth returns at once. So in this wide middle distance, survival without protection remains very short. Useful consciousness lasts only seconds because there is no oxygen and no pressure fit for life. Biological survival may continue briefly after consciousness is lost, but not for long unless rapid repressurization and oxygen are restored. The brighter sun, the growing warmth of direct light, the long calm emptiness, and the slow motion of worlds through black space do not make this region kinder than the outer dark. They only change its appearance. Beneath that appearance it remains open vacuum crossed by radiation and silence, a place through which humans may travel only inside fragile, carefully maintained shells of Earth-like conditions. Mars begins to look different from the worlds beyond it long before a person reaches the ground. From orbit, it has deserts, canyons, volcanoes, polar ice, dust storms, and a horizon that resembles a planet in the familiar rocky sense. It is not a gas giant and not an icy dwarf. It is a terrestrial world with a real surface, a day close to Earth's in length, and seasons shaped by its tilted axis. Yet the first inward region of Mars is not the ground itself. It is the thin envelope of air above that ground, an atmosphere so sparse that it changes the meaning of exposure. A human body entering Mars without protection is no longer in full vacuum, but it is still in conditions far too thin and chemically wrong to sustain life for more than a very brief span. The Martian atmosphere is made mostly of carbon dioxide, with nitrogen and argon forming much of the rest, plus traces of oxygen and water vapour. The key fact is not simply that oxygen is scarce, it is that the total pressure is very low, only a small fraction of the pressure at Earth's sea level. This means Mars does have weather, clouds, wind, and air moving over land, but that air is too thin for human lungs to use. Breathing it would not supply enough oxygen, and the low pressure itself would place the body in severe danger. Mars is therefore a world where the presence of an atmosphere can mislead the imagination. There is air, but not living air. There is sky, but not a sky that makes exposure survivable. A person arriving in the open Martian air without a suit would remain conscious only briefly. The body would still have some oxygen already circulating in the blood, and that reserve would support awareness for a short interval measured in seconds. After that, thinking would fade, coordination would fail, and consciousness would be lost. The experience would differ from open space in one important way. Because there is some surrounding gas, the body is not in complete vacuum. Even so, the pressure is low enough that ordinary human function cannot continue. Moisture on exposed surfaces would behave abnormally. The lungs would not perform normal gas exchange. The body would begin to fail from a combination of oxygen deprivation and low pressure long before any longer process of cold injury could define the outcome. Cold remains a major feature of the Martian atmosphere. Mars is farther from the Sun than Earth, and its thin air does little to hold heat. Temperatures vary widely by place, season, time of day, and dust conditions. Near the equator on a sunny afternoon, surface temperatures can rise to values that may seem surprisingly moderate, but the atmosphere around them remains thin, and the warmth does not mean safety. At night, and in higher or colder regions, Temperatures fall sharply. Because the air is so sparse, it cannot carry heat to or from the body as strongly as Earth's atmosphere can. Yet contact with cold surfaces and the overall thermal environment still threaten life quickly. The body on Mars is therefore not simply freezing in the ordinary sense. It is exposed to a world where pressure, gas chemistry, and temperature all depart from human needs at once. The sky would not be black in the same way as open space. Mars has enough atmosphere for light to scatter, and that gives the planet its butterscotch, salmon, and dusty tones depending on conditions and the amount of fine material in the air. During the day, the sky can appear reddish or tawny, while around sunset and sunrise certain conditions create blue tones near the sun because of the way dust scatters light. For an exposed person, this visible sky might briefly create the illusion of a place almost within reach of habitability, but the illusion would not last. The first breath would fail to provide oxygen. The body would soon understand, at the most fundamental level, that the Martian atmosphere is present without being usable. Dust is part of this atmospheric region even before the surface itself becomes the main focus. Mars is famous for fine dust suspended in the air, from local gusts to vast storms that can cover much of the planet. The thinness of the air limits the force that wind can exert compared with equal wind speeds on Earth. But the dust still matters because it is pervasive, electrostatic, and capable of coating equipment and reducing visibility. In unprotected exposure, however, dust is not the immediate killer. It belongs more to the engineering problem of living on Mars than to the first minute of bare survival. The body would lose consciousness from lack of oxygen before dust inhalation or abrasion became the main issue. The lower gravity of Mars, weaker than Earth's, also shapes this atmospheric region. A suited person would move with longer strides and reduced weight. Dust lofted by movement would settle differently. Falling would feel different from falling on Earth, but unprotected survival is not meaningfully improved by lower gravity. The lungs still need oxygen. The bloodstream still needs proper pressure. The brain still fails after only a short interruption in supply. Gravity changes motion, not the fundamental chemistry of life. Radiation also matters more on Mars than on Earth, because Mars lacks a global magnetic field like Earth's, and has only a thin atmosphere to block incoming high-energy particles. Over long stays, this becomes a major challenge for explorers and settlers. Solar storms and cosmic rays raise risks to tissue and increase the need for shielding in habitats and spacecraft. Yet in the first moments of sudden exposure, radiation remains secondary to the immediate crisis of respiration and pressure. It is part of the total harshness of Mars, but not the fastest reason an exposed person dies. So the outer region of Mars, its thin atmosphere above the ground, offers only a little more physical support than vacuum and nowhere near enough for a human being to survive unaided. A person without a suit lasts only a short time. Useful consciousness is measured in seconds. Death follows soon after unless pressure and oxygen are restored quickly. The presence of air, weather, clouds, and a coloured sky does not change that truth. Mars is close enough to Earth in appearance to feel almost welcoming from a distance, yet its atmosphere remains too thin, too cold, and too poor in oxygen to sustain life. In this first Martian region, survival ends not because the planet is violently dramatic, but because its air is only a faint imitation of what the body requires every second it remains alive. The Martian surface is a place of rock, dust, frost, and distance. It has valleys cut long ago by flowing water, volcanoes larger than any on Earth, dunes shaped by thin winds, and plains where landers have rolled across ancient ground under a salmon-coloured sky. Of all the worlds beyond Earth, it is one of the easiest to imagine as a place where a person might stand and look around. That familiarity is part of what makes it dangerous to picture incorrectly. The ground is real, the horizon is clear, and the landscape often resembles a dry desert or cold polar plain. Yet none of this makes the surface naturally survivable. Once the path moves fully from Martian air to Martian ground, the question becomes not whether there is a place to stand, but how long the body can remain alive on that place without protection. The answer remains very brief. On the surface of Mars, the atmosphere presses only weakly against the body. It is thin enough that liquid water is unstable in the open under most conditions. This matters deeply for human biology because the body depends on water remaining liquid inside tissues and across moist membranes. At Martian surface pressure, exposed moisture in the mouth, eyes, and lungs behaves abnormally. It does not mean the whole body instantly boils away. The skin and internal structure still hold fluids in place to some degree, but the low pressure places the body in an environment beyond its normal operating range, and this begins to damage function immediately. The lungs cannot perform useful gas exchange. Any attempt to breathe the air only moves carbon dioxide-rich gas in and out without supplying meaningful oxygen. Consciousness would begin to fade within seconds. The ground itself changes the experience of exposure. In open space, the body floats in vacuum. On Mars, the body touches stone, dust, or frost. That contact creates a more direct relationship with cold surfaces and terrain. Depending on location and time of day, the ground can be intensely cold, especially before dawn, at high latitudes, or during winter, even where sunlight warms the uppermost soil somewhat. The warmth is not like Earth's because the atmosphere above is too thin to provide a stable thermal setting. Bare skin against Martian ground would freeze and injure quickly. If a person fell face down into fine dust, the contact would not suffocate in the ordinary earthly sense because the main suffocation is already happening through lack of oxygen in the air. Instead, the ground would add cold, abrasion, and obstruction to a body already losing control. Martian dust is one of the defining features of the surface. It is fine, dry, and rich in oxidized iron compounds that give Mars much of its red color. It clings to equipment, covers solar panels, works into joints and seals, and remains suspended in the atmosphere during storms. On the surface, that dust is not just scenery. It is part of what every step and every movement disturbs. A suited human would kick it up in small puffs under weaker gravity, and a rover wheel would leave crisp marks in it. An unprotected person would have little time to notice such details, but they still matter because the dust is part of the physical reality of being there. It would gather on skin and clothing, enter the mouth and nose if breathing were attempted, and coat surfaces around the body. Yet again, dust is not the first cause of death. It complicates exposure, while low pressure and lack of oxygen remain the central forces. The Martian sky from the surface also shapes the scene in a way that is much more familiar than anything on the giant planets. There is a visible horizon, and beyond it rise crater rims, mesas, dune fields, volcanic slopes, or the edge of a plain scattered with stones. Light changes through the day. The sun moves across the sky. Thin clouds of water ice can form. Dust devils can move across the landscape as narrow, spinning columns. These details make Mars feel accessible, almost like a place where human presence is only a matter of endurance. But the body does not live on appearances. It lives on chemistry and pressure. However natural the scene may look, the air remains too thin and too oxygen-poor to keep the brain functioning. Temperature on the surface varies widely, at some equatorial locations during the warmest part of the day. The air and ground may rise to values that sound almost tolerable. Yet these moments do not make the environment safe. The body cannot use the atmosphere because pressure remains too low and oxygen remains nearly absent. At night, temperatures fall sharply, often to severe cold that would rapidly threaten exposed tissue and eventually the whole body. Because the atmosphere is so thin, heat does not move through it in the same way it does on Earth. The body radiates heat and exchanges it with the ground and sunlight, but the overall setting remains one of thermal instability. A person exposed on the Martian surface dies first from hypoxia and low pressure, not because the world waits long enough for simple freezing to finish the work. The lower gravity of Mars slightly eases the body's weight, but that does not extend survival in any meaningful way without life support. A person might stumble differently, fall more slowly, or rise from the ground with less effort if conscious and protected. But in sudden exposure, coordination would fail so quickly that the graceful possibilities of lower gravity would be lost almost at once. The body is not dying because it is too heavy to move. It is dying because oxygen is absent and the air is too thin to support normal internal function. Water on the Martian surface is mostly locked as ice or as bound material within minerals and soil. Under present surface conditions, stable liquid water is rare and generally short-lived. This matters because the surface is dry in a way that goes beyond desert dryness. It is not simply a landscape lacking rivers. It is a landscape where the pressure and temperature together make open liquid water difficult to sustain. For human survival, this means there is no native supply that can simply be gathered and used without substantial processing and protection. The surface offers land but not habitability. So the Martian ground, for all its familiarity, remains a lethal place for an unprotected human body. A person would likely remain conscious for only a short span of seconds. Death would follow soon after, unless oxygen and pressure were restored rapidly. Cold ground, thin dusty air, wide deserts, and visible horizons do not change the central truth. Mars has a real surface, but that surface lies under an atmosphere too sparse to preserve life, and in a climate too unstable to support exposed human biology. The body can stand there briefly, but it cannot belong there without carrying its own small Earth around itself. Earth is the exception because it does not force the human body to fight for the simplest conditions of life. It provides those conditions continuously and so completely that they can seem invisible. A person standing on Earth's surface is surrounded by air at a pressure that keeps water stable in the body, supports breathing, and allows the lungs to exchange gases in a steady rhythm without mechanical help. The atmosphere contains abundant nitrogen and enough oxygen to sustain the brain, the muscles, and every organ that depends on constant cellular energy. Liquid water is common. Temperatures, across much of the surface and through much of the year, remain within a range that life can tolerate. The planet does not need to be made habitable by machinery before the body can exist upon it. It is already habitable, and that fact becomes clearer when compared with every world beyond and within its orbit. The air itself is one of Earth's quiet achievements. It is dense enough to protect the body from the lethal effects of vacuum, but not so dense that every movement becomes a struggle. It carries sound, scent, moisture, and heat. It allows clouds to form, rain to fall, and winds to move energy from one region to another. It softens sunlight through scattering, turning the sky blue by day and diffusing light so that shadows are rarely absolute. For a human being, this means the outside world is not merely visible but physiologically workable. Breathing is possible without equipment. Speech, hearing, and ordinary movement all depend on the presence of air, and on Earth that presence is so normal that it often escapes notice. Pressure at the surface is equally important. It holds the body within a narrow physical range where fluids remain where they should. Lungs inflate normally, and blood chemistry can be regulated without crisis. In low-pressure environments like Mars or open space, exposed moisture behaves abnormally and gas exchange fails. On Earth, the pressure envelope is so well matched to human biology that ordinary existence becomes possible from birth onward. The body develops within it, grows within it, and ages within it. There is no need for a suit, habitat, shell, or artificial circulation system simply to remain conscious in the open air. This is an extraordinary condition when measured against the rest of the solar system. Earth's water cycle adds another layer of support. Water exists here in all three familiar states and moves continuously between ocean, atmosphere, ice, soil, rivers, and living tissue. This matters not only because humans must drink water, but because liquid water shapes climate, chemistry, and biological possibility across the whole surface. Oceans store heat and moderate seasons. Clouds reflect sunlight and move fresh water across continents. Soil retains moisture for plants. Ice stores part of the planetary water budget and influences global reflectivity. The human body, being itself largely water, belongs naturally in a world where water is stable at the surface. On most other planets and moons, liquid water is absent from ordinary open conditions, locked away, frozen, vaporized, or crushed into unfamiliar states. On Earth, it is part of daily life. Temperature is another reason Earth functions as the exception. It is not uniformly mild. Deserts can burn with heat. Polar regions can kill by cold. Mountains, storms, droughts, and floods all remind life that habitability does not mean comfort everywhere at all times. Yet within the broad planetary average, Earth remains moderate enough for liquid water and for biological systems to persist over immense spans of time. Day and night cycles, ocean circulation, atmospheric mixing, and greenhouse warming together create a world where large portions of the surface remain within living range. The body still needs clothing, shelter, and culture to navigate the full variety of climates. But it does not need a pressurized suit merely to walk outside and breathe. Earth also protects life from above. Its atmosphere blocks much of the harmful ultraviolet radiation coming from the sun, and its magnetic field deflects many charged particles that would otherwise increase radiation exposure at the surface. These systems are not perfect shields, but they greatly reduce the continuous biological stress that life would face in open space or on a planet with little atmospheric and magnetic protection. Mars, for example, allows far more radiation to reach the surface because its atmosphere is thin and its global magnetic field is absent. Earth, by contrast, places a layered buffer between living tissue and the harsher parts of the cosmic environment. Gravity on Earth provides another form of deep familiarity. It is strong enough to hold a substantial atmosphere and oceans, yet not so strong that the body is pinned into immobility. Human muscles, bones, balance, circulation, and posture all develop around this persistent downward pull. In weak gravity, as in orbit or on Mars, the body begins to change over time. Bone is lost, muscles weaken, fluids shift. On Earth, gravity is not a threat in ordinary life. It is constant shaping force that the body knows how to meet. Walking, standing, lifting, and sleeping all take place within a gravitational setting that human anatomy has adapted to over evolutionary time. This does not mean Earth guarantees indefinite survival. The body remains fragile. It still depends on food, clean water, moderate temperature, rest, and protection from injury and disease. A person without shelter in a blizzard, desert, flood, or fire can die quickly even here. Earth's habitability is broad, not universal in every moment and location, but compared with every other planet, the distinction remains decisive. On Earth, death from environmental exposure is usually the result of an extreme condition within a fundamentally habitable world. Elsewhere in the solar system, death from exposure is the normal result of worlds that are fundamentally uninhabitable without technology. So the answer for Earth is not a short survival estimate, but a different kind of truth. A person lasts here not for seconds or minutes, but for an ordinary lifespan, because the environment continuously supports the chemistry of life. Air can be breathed, pressure remains stable, water is available, temperatures are moderate across much of the planet. Radiation is partly shielded, gravity is familiar. Earth does not remove all danger, but it removes the need to carry an artificial world around the body every second one wishes to remain alive outdoors. In the inward journey through the planets, this makes Earth the calm central exception, the one place where survival is not a brief resistance against alien conditions, but the natural starting state from which every other comparison is made. Venus above the clouds is the first inward region where the pattern begins to change in an unexpected way. From far away, Venus is often imagined as the most hostile of the rocky planets, because its surface is hotter than Mercury's and buried under enormous pressure. Yet high above that surface, in the upper cloud region, the planet passes through layers where temperature and pressure become less extreme than they are below. This does not make the region safe for an exposed human body. It remains entirely unbreathable, chemically dangerous, and deeply unlike Earth. Still, it is one of the few places away from Earth where some of the basic physical values begin, for a limited range of altitude, to resemble the values that human life prefers. The resemblance is incomplete and fragile, but it gives this region a distinct character. Survival here is not determined by heat and crushing weight alone. It is shaped by altitude, acid, pressure, and the wrong atmosphere. The visible globe of Venus is wrapped in bright cloud. Those clouds are thick, global, and highly reflective, which is why Venus shines so brilliantly in Earth's sky. They are composed mainly of droplets of sulfuric acid suspended within a dense atmosphere dominated by carbon dioxide, with nitrogen as the next most important component. Above and within the upper cloud region, sunlight is strong because Venus is closer to the Sun than Earth is, yet much of that light is reflected or scattered by the vast cloud cover. The result is a world of diffuse brightness, pale haze, and layered atmosphere rather than open blue sky. To a human observer in a protected craft or balloon, the upper clouds could appear almost softly luminous. To an exposed person, that luminous air would remain immediately dangerous. Unlike Mars, Venus provides no shortage of atmospheric pressure at most heights. In fact, pressure is one of the defining features of the planet. Near the surface it is enormous, but at higher altitudes it decreases, and there are layers where pressure approaches values familiar from parts of Earth's lower atmosphere. This matters because it changes one part of the survival problem. In some of these upper regions, the body would not be confronting near vacuum conditions. Moisture would not begin to boil simply from low pressure in the way it does on Mars or in open space. Yet this does not create habitability. The air is almost entirely carbon dioxide and contains effectively no breathable oxygen. A person exposed there would still lose consciousness within a short time because respiration would fail. The lungs may inflate and deflate under more manageable pressure than on Mars, but they would still be drawing in the wrong gas. Temperature in the upper cloud region also changes with altitude. Higher up, conditions can be extremely cold, while somewhat deeper layers become warmer. There exists a band of altitude where temperatures are far less severe than those on the surface below, even reaching values that might sound almost moderate by planetary standards. This fact has led scientists to note that the upper atmosphere of Venus is, in a narrow physical sense, more Earth-like than the surface of any other planet. But this observation must be handled carefully. Earth-like here does not mean human safe in the open. It means only that pressure and temperature can briefly approach ranges that do not instantly destroy every material and every mechanism. The chemistry remains hostile. The clouds and haze contain sulfuric acid droplets capable of causing severe chemical injury. The atmosphere is still overwhelmingly carbon dioxide. There is still no oxygen to sustain the brain. The acid is one of the defining hazards of this region. Sulfuric acid in the cloud droplets would attack exposed tissues, especially the eyes, airways, and skin. The extent and speed of injury would depend on droplet concentration, exposure time, and exact altitude. But there is no natural version of this environment that a human body can tolerate directly. Even if pressure and temperature at a particular height were closer to familiar values, the chemistry would still be fatal. An exposed person might remain conscious slightly longer than in vacuum, because pressure itself is less immediately catastrophic. But not for long. Oxygen deprivation would still dominate. Chemical irritation and damage would begin at once. Breathing the atmosphere would not support life and would instead harm delicate tissues almost immediately. The upper atmosphere of Venus is also dynamic. Winds at cloud level move rapidly around the planet in a pattern often called superrotation, where the atmosphere circles the planet much faster than the solid planet turns beneath it. This means that the upper cloud region is not a still suspended layer. It is a fast-moving aerial environment of haze, acid droplets, and shifting light. A person unsupported there would not stand or float comfortably in a quiet sky. The body would be carried through a chemically aggressive atmosphere under strong winds, with little visibility and no breathable air. Even if temperature and pressure were locally less extreme than expected, motion and chemistry would ensure that the region remained entirely unfit for exposed survival. Light in this region would have a very different character from that of Mars or Earth. The thick cloud layers would scatter sunlight into a broad brightness, rather than a sharply defined sky. There would be no distant clear horizon like a desert planet and no black background like open space. Instead, there would be glowing haze, yellow-white cloud, and muted contrast. Deeper layers would grow dimmer and more enclosed as the clouds thickened. Above, brightness would still be filtered through aerosol and vapor. The whole atmosphere would feel visually soft and physically hostile at the same time. So the survival answer above Venus's clouds is more nuanced in structure, but not gentler in outcome. The region is important because it shows that Venus is vertically layered in a way that matters. Some upper levels are far less extreme than the inferno below, and in those levels pressure and temperature can approach values more familiar to life from Earth. Yet this does not allow an exposed human body to survive. The air remains unbreathable, oxygen is absent, sulfuric acid fills the clouds, and high winds drive the atmosphere around the planet. A person without protection would still remain conscious only briefly before hypoxia caused collapse, with chemical injury beginning at the same time. Venus above the clouds is therefore not a refuge. But it is a reminder that planetary hostility can vary sharply with altitude, and that even a somewhat softer physical range means very little when the atmosphere itself is made of the wrong substance. Venus at the surface is not merely inhospitable, it is physically overwhelming in almost every way a rocky planet can be. The ground lies beneath a vast atmosphere of carbon dioxide so dense that it presses on the surface with a force many times greater than the pressure at Earth's sea level. The heat is intense enough to melt lead. The light that reaches the ground has been filtered through thick cloud and deep haze, leaving a dim yellow-orange world of rock, dust, and air so heavy that it behaves almost like a burden laid directly upon every exposed object. This is the inward region where the question of survival becomes shortest and most severe among the solid planets. A human body placed unprotected on the surface of Venus would not endure for more than a very brief instant before heat, pressure, and toxic air together made life impossible. The atmosphere at the surface is composed mostly of carbon dioxide, with nitrogen as the next largest component and traces of other gases, including sulfur-bearing compounds. There is essentially no oxygen for human respiration. That alone would make survival impossible. But on Venus the lungs face a problem even before oxygen is considered. The pressure at the ground is so great that normal breathing cannot occur at all. A human chest and respiratory system are adapted to a narrow pressure range near Earth's surface. On Venus, the surrounding atmosphere presses with enormous force. Even if breathable gas was somehow present, which it is not, the body could not simply function normally in such a crushing environment without specialized protection. The heat at the surface is equally decisive. Venus is hotter at the ground than Mercury is under direct sunlight, despite Mercury's closer distance to the Sun, because Venus's dense carbon dioxide atmosphere traps heat through a runaway greenhouse effect. Surface temperatures are commonly around several hundred degrees Celsius, hot enough to damage living tissue almost instantly and to destroy many materials rapidly. Skin would burn, eyes would be injured at once, moist tissues would suffer catastrophic thermal damage. The internal temperature of the body would begin rising immediately, but it would not take time for whole body heating to become the main story. The outer tissues and respiratory surfaces would already be devastated by the surrounding temperature and pressure combination. Unlike Mars, where low pressure threatens the body by offering too little external support, Venus crushes from the opposite side. The body is built to contain pressure and to work within a moderate balance between inside and outside. On Venus, that balance is overwhelmed. Gases in the lungs and airways would be severely affected. Circulation would be placed under extraordinary stress. Every exposed surface would confront a dense hot atmosphere pressing and heating at once. This is not a place where one could remain conscious for several seconds while slowly realizing the danger. The danger is immediate at contact. It acts through the whole body from the first moment. The light at the surface would not resemble the brilliant white sunlight of space or the open skies of Earth and Mars. Thick cloud above blocks direct view of the sun and scatters the incoming light through the dense atmosphere. As a result, the ground is dim by daylight standards, bathed in an orange-brown glow. Rocks and plains would appear through heavy air and haze. Some landers sent by the Soviet Union survived only briefly in these conditions, and the images returned from Venus show a stony landscape beneath a suffocating sky. Those machines were built with special pressure vessels and cooling systems, yet even they endured only for limited spans before the environment overcame them. An exposed human body would have no such resistance at all. The surface itself is made of volcanic plains, fractured rock, and scattered highlands. Radar mapping has revealed broad lava-covered regions, shield volcanoes, deformed terrain, and impact structures. It is a genuine planetary landscape, but it is hidden beneath an atmosphere so dense and hot that ordinary geological familiarity offers no comfort. Ground underfoot does not help when the air itself is crushing, and the temperature is high enough to cook tissue. On Earth, standing on solid land usually brings safety from falling and access to breathable air. On Venus, the land is simply the bottom of a lethal ocean of hot gas. Wind at the surface is not necessarily violent in speed compared with high-altitude Venusian winds, because the dense lower atmosphere moves differently and can be relatively slow in meters per second. Yet even modest motion in such dense air can exert substantial force. More important, the lower atmosphere does not need to be stormy to be deadly. A calm day on Venus remains unsurvivable. The body does not need to be struck by flying debris or torn by wind. It only needs to be immersed in the atmosphere itself. The air is enough. The chemistry of the lower atmosphere adds further injury. Although the sulfuric acid clouds are mainly an upper atmosphere feature and tend not to remain stable as liquid droplets all the way to the surface, sulfur-bearing compounds still contribute to the corrosive character of the environment. Materials degrade. Metals and seals face chemical stress. For living tissue already being destroyed by heat and pressure, these chemical details are secondary but still part of the total hostility of the planet. Venus does not kill by one mechanism alone. It combines many and removes every possibility of open survival. So the answer on Venus's surface is the shortest among the rocky planets. An unprotected human would survive only for a moment. Not because one isolated injury occurs first, but because all necessary conditions for life are absent at once and replaced by their opposites. There is no oxygen. The pressure is crushing. The heat is extreme. The atmosphere is toxic. The light is dim and filtered through dense haze, but that visual softness hides nothing. The body would be overwhelmed almost immediately, with consciousness lost at once or nearly so, and death following essentially without delay. Venus at the surface is therefore the clearest example of a terrestrial world that looks like a planet in shape and ground, yet behaves like a furnace under weight. A place where the human body has no interval of resistance worth calling survival. Mercury in sunlight is a world of bare stone under relentless exposure. It lies closest to the sun, and on its day side the surface receives intense solar energy, without the moderating benefit of a substantial atmosphere. There are no clouds to reflect and redistribute heat, no winds to carry warmth across the land, and no blue sky to soften the brightness overhead. The planet presents a stark landscape of craters, cliffs, plains, and ancient impact scars lit by a sun that appears much larger and more forceful than it does from Earth. At first this might suggest that heat alone defines survival there, but the truth is more complete. Mercury's sunlit side combines high surface temperature, hard radiation exposure, and a near-total lack of atmospheric pressure. The body does not simply stand in hot weather. It stands in something much closer to open space, with blazing sunlight pouring down onto rock. Mercury has only an extremely tenuous exosphere, a very thin scattering of atoms rather than a true atmosphere. This exosphere contains traces of elements such as sodium, potassium, oxygen, helium, and hydrogen. But it does not function as air in any human sense. It cannot be breathed. It does not provide pressure for the lungs. It does not shield the body from radiation or moderate temperature across the surface. A person exposed on Mercury's day side is therefore in near vacuum, much as they would be in open space or on many airless moons. The first danger remains the same one already seen beyond Neptune and between the planets. The lungs cannot draw in oxygen. Consciousness begins to fade within seconds. The body encounters not a hostile breeze or poisonous gas, but the near absence of any supportive medium at all. Pressure is almost non-existent, and that fact governs the first moments of exposure. Moisture in the mouth and airways would begin to behave abnormally under such low pressure. The body would swell somewhat, though it would not explode. The lungs would fail as organs of gas exchange because there is no useful surrounding gas and no pressure fit for breathing. If the breath were held, lung injury could occur from expanding internal gas. If air were allowed to escape, the body would still lose useful consciousness in a short span as oxygen in the blood ran out. This remains the immediate biological reality of Mercury. Despite the intense sunlight, the body dies first from lack of air and pressure, not because it instantly burns to ash. Yet Mercury adds a powerful thermal and radiative burden to that same near-vacuum exposure. On the day side, surface temperatures can become extremely high, especially near the equator when the sun stands high in the sky. Rock absorbs solar energy and grows intensely hot. Any contact with the ground would rapidly injure tissue. Bare skin touching sunlit stone or metal equipment heated by direct sunlight would suffer severe burns. Unlike Earth, there is no atmosphere to scatter sunlight broadly or carry heat into a moving mass of air. Solar energy arrives directly. Surfaces either absorb it, reflect it, or re-radiate it into space. This creates a harsh contrast between illuminated and shadowed areas. But on the day side, the dominant impression is overwhelming brightness and steady thermal loading. The sun itself would look striking from Mercury's surface. It would appear larger than it does from Earth, and its light would feel less filtered, more raw. Shadows would be intensely black at their edges because there is no atmosphere to soften them. The sky above would remain black even in full daylight, as it does on the moon, because there is no substantial air to scatter light and create a blue dome. This produces one of the strangest visual combinations in the solar system. Brilliant sunlight falling across crater walls and plains beneath a black sky. For a human observer in a suit, it would be spectacular. For an unprotected body, the scene would last only moments before consciousness faded. Radiation is another defining part of Mercury's day side. The planet has only a weak magnetic field compared with Earth's, and without a substantial atmosphere there is little shielding from solar radiation and energetic particles. Ordinary sunlight itself, including intense ultraviolet, would stress exposed tissue, while high-energy radiation poses longer-term hazards to cells and organs. In the first moments of direct exposure, radiation is still not the fastest killer. Suffocation from vacuum-like conditions comes first. But Mercury's proximity to the Sun ensures that radiation is a much larger part of the total danger than it is in more distant airless regions. Even a protected visit requires careful thermal and radiation control. An unprotected one is impossible. The ground on Mercury is real and solid, unlike the cloud tops of the giant planets, but this only changes the geometry of exposure, not its survivability. A person can stand on rock, move through craters, and cast a shadow across regolith and broken stone. The low gravity, stronger than that of the Moon but much weaker than Earth's, would make motion feel lighter for a protected explorer. Steps would carry farther. Falls would be slower. But lower gravity does not compensate for the absence of air. The body still requires oxygen, pressure, and temperature regulation. Mercury provides none of these. It offers land without life support. The long Mercurian day also matters because the planet rotates slowly relative to its orbit, creating prolonged periods of heating and cooling across the surface. This means a location in sunlight can remain under intense solar exposure for a very long time. The surface has ample time to absorb energy and grow dangerously hot. There is no atmospheric circulation to transport that heat efficiently around the globe. Instead, the planet's surface conditions are set largely by direct solar illumination and local topography. Sunlit crater rims and plains can become scorching, while nearby shadows remain much cooler. But for an exposed person, these local differences do not create a safe zone. Even in shadow, the lack of atmosphere keeps the body in near vacuum. The thermal setting changes, but the respiratory setting does not. So Mercury in sunlight is lethal in layered but very direct ways. A person without protection would lose useful consciousness within seconds, because there is no breathable atmosphere and almost no pressure. Death would follow soon after, unless immediate rescue restored oxygen and pressure. At the same time, intense sunlight and extreme surface heat would begin burning exposed tissue and loading the body with thermal stress. Radiation from the nearby sun would add to the hostility of the environment. The visual clarity of black sky, bright rock, and hard-edged shadow does not imply simplicity. It reveals a planet where land exists in open exposure to space and solar fire. On Mercury's day side, survival is brief because the body is placed on hot stone under a fierce sun, while still suffering the same vacuum-driven failure that governs almost every airless world. Mercury in darkness becomes a different world without becoming a kinder one. On the night side, the fierce direct heating of the sun disappears and the surface releases its stored warmth into space. Because Mercury has almost no true atmosphere, there is no blanket of air to hold heat close to the ground, no winds to carry warmth from the day side, and no weather to soften the contrast between illuminated and unilluminated terrain. The result is a landscape of extreme cold under a black sky, a place where craters, ridges, and plains fall into still shadow, while the planet continues its slow rotation near the sun. In this inward region, the body is spared the immediate burn of direct solar heating, but it's still exposed to the same near vacuum that makes airless worlds deadly. The danger changes in temperature, not in habitability. The first moments of unprotected exposure on Mercury's night side are governed, as they are on the day side, by the absence of a real atmosphere. The exosphere remains far too thin to support breathing or provide meaningful pressure. A person standing in darkness there would not inhale useful air. The lungs would receive nothing that could maintain oxygen in the blood. Consciousness would begin to fade within seconds. The body would swell modestly under the low pressure. Moist surfaces in the mouth and airways would behave abnormally. If the breath were held, lung damage could occur from pressure imbalance. If it were released, the result would still be rapid oxygen loss and collapse. The cold is severe, but the body does not remain conscious long enough for cold alone to tell the full story. The main immediate cause remains the same vacuum-driven failure found on other airless worlds. What changes most strongly in darkness is the thermal environment of the surface. Mercury's long nights allow the ground to cool to extremely low temperatures. Rock and dust that spent long periods under intense sunlight eventually radiate much of their heat away once the sun is gone. In permanent shadow, especially in deep polar craters where sunlight may never reach the floor, temperatures can remain so low that water ice delivered long ago by comets or formed through other processes can persist. This is one of the most striking findings about Mercury. A planet closest to the Sun also contains some of the coldest stable surface conditions in shadow. For a human body, this means the night side offers not relief, but another extreme. Instead of standing on hot bare stone under direct sunlight, The body stands on frozen ground, exposed to deep cold and near vacuum at the same time. Bare skin touching the night-side surface would freeze rapidly. Thermal energy would flow out of the tissue into the colder material. Metals and shaded rock could become dangerous to contact almost at once. Over a longer interval, the whole body would cool by radiating heat into the black surroundings and by contact with cold ground. But whole body freezing would still not be the first barrier to survival. The person would already have lost consciousness from lack of oxygen before general cooling completed its work. This distinction matters because it separates appearance from physiology. The night side looks like a frozen death. And in one sense it is. But biologically the body still dies first because Mercury offers almost no atmosphere. The visual character of this region would be stark even by planetary standards. Without sunlight directly overhead, the ordinary night side is very dark, illuminated mainly by starlight and by faint reflected light from surrounding terrain or from the distant sun if near the terminator. In deeper shadow, especially within crater interiors, vision would become extremely limited. The sky would remain black, not because it is night in the earthly sense, but because there is no atmosphere to scatter even the small amount of available light. Stars would appear sharp and steady. The sun, though absent from local view, still rules the broader geometry of the planet, yet its warmth does not reach these shadowed regions in a useful way. Mercury's darkness is therefore not like a cool evening on Earth. It is an open-air exposure to space with solid ground below. Radiation on the night side is different in balance from the day side, but not absent. Without direct solar illumination, the immediate thermal and light burden from the sun is removed. Even so, the body remains exposed to the broader space environment, including cosmic radiation and energetic particles not stopped by any substantial atmosphere. Mercury's weak magnetic field offers only limited help compared with Earth's. In the first minute of unprotected exposure, radiation is still not the fastest danger, yet it remains part of the larger truth that Mercury's night side, like its day side, belongs more to space than to any habitable planetary environment. The low gravity again affects motion but not outcome. A protected human might move lightly over cold crater rims, leap across darker regolith, and traverse shadowed slopes with less weight than on Earth. But lower gravity does not create survivability where air is absent. It changes the style of exploration, not the basic terms of life. The body still requires pressure and oxygen every second it remains conscious. Mercury's night side gives neither. The permanently shadowed craters near the poles deserve special attention because they reveal the sharpest version of this dark Mercurian world. These craters can preserve water ice because sunlight never reaches their floors. Radar observations and spacecraft measurements support the presence of such ice deposits. This gives Mercury an inward complexity that seems almost paradoxical. Near the hottest part of the solar system's terrestrial region, there exist pockets of lasting cold capable of holding frozen volatiles. For human survival, however, this changes very little. Ice does not mean open habitability. A person without protection in these shadowed craters would still die quickly from lack of oxygen and pressure, with intense cold adding severe tissue injury. So Mercury in darkness remains only briefly survivable, just like Mercury in sunlight, though for a different combination of immediate sensations. Useful consciousness would last only seconds because the exosphere cannot support breathing and the pressure is effectively absent. Death would follow soon after unless rescue restored a proper atmosphere at once. The difference is that night removes the burning glare and replaces it with deep cold, black shadow, and frozen ground. Mercury's dark side is therefore not the opposite of danger but another face of the same fundamental truth. The planet offers solid land, but whether under blazing sun or in profound darkness, that land lies exposed to space. On the night side, the human body does not burn. It suffocates in near vacuum while standing on a world cold enough in shadow to preserve ancient ice. Closer to the sun than any planetary surface can bring a human body. The inner solar system becomes less a place of worlds and more a place of radiance. This final inward region is not a ground to stand on, but an approach into the sun's overwhelming environment, where light, heat, and charged particles intensify until the idea of ordinary exposure loses meaning. Mercury already reveals part of this truth. It stands on the edge of a domain where airless rock endures under fierce solar energy. But inward from Mercury there is no solid refuge at all, only expanding brightness, deepening radiation, and the increasing force of the solar wind. The stream of charged particles that flows outward from the sun through space. In this region, survival is not measured against land or weather. It is measured against raw stellar output, and the body has almost no resistance to it. The sun is not a burning surface in the everyday sense. It is a star, a sphere of plasma, which is matter so hot that electrons and atomic nuclei no longer remain bound together in ordinary atoms. Its visible surface, called the photosphere, is only the layer from which most visible light escapes. Above it lie the chromosphere and the corona, outer regions of hot plasma structured by magnetic fields and shaped by loops, streams, and eruptions. None of these layers can be approached by an exposed human body in any meaningful way. Long before any near encounter with the sun itself, the surrounding space becomes lethal. The body does not need to touch solar plasma to be destroyed by the sun. It only needs to move far enough inward that radiation and heat exceed any natural tolerance. The first limit still begins with pressure and breathing if the body is directly exposed. The space between Mercury and the sun remains essentially vacuum. There is no atmosphere to breathe, no pressure to support the lungs, and no medium that can sustain ordinary human physiology. An unprotected person placed there would lose useful consciousness within seconds for the same reason they would in deep space beyond Neptune. Oxygen in the blood would be consumed and not replaced. The lungs would fail as organs of exchange. Moisture at exposed surfaces would behave abnormally under low pressure. In this basic respiratory sense, the inner solar region remains space, and space remains immediately deadly. But near the sun, the thermal and radiative burden rises far beyond what was described for the outer and middle reaches of the solar system. Sunlight grows more intense as distance decreases. This is not a gentle increase. It becomes a rapidly strengthening load of energy striking every exposed surface. Skin and eyes would be damaged almost at once. Tissues would heat under direct radiation. Equipment not designed for this environment would fail quickly as it absorbed more energy than it could reject. The body, already suffocating in vacuum, would also begin suffering severe burns and thermal stress from the sun's concentrated output. There would be no need to wait for contact with a planetary surface or a pool of molten material. Light itself, in sufficient concentration and proximity, becomes part of the destructive environment. Radiation here includes more than visible light and warmth. The sun emits across a broad spectrum, including ultraviolet and X-ray radiation, and it drives a constant flow of charged particles outward through the heliosphere. During solar eruptions, this outflow can become more intense and more dangerous, even under quieter conditions. The near-solar environment is harsh. A human body requires layers of protection against ionizing radiation because such radiation damages cells, breaks chemical bonds, and harms delicate tissue, especially in the eyes. skin, and blood-forming organs. Near the Sun, radiation is not just a long-term background risk. It becomes one of the defining conditions of the region. The solar wind also changes character as one moves inward. It remains a very tenuous flow by everyday standards, not a wind that pushes like air on Earth, but it carries energy, magnetic structure, and charged particles across interplanetary space. Spacecraft sent close to the Sun, such as NASA's Parker Solar Probe, do not enter an ordinary atmosphere. They move through an environment shaped by plasma and magnetic fields, where heat shielding and careful orientation are essential to survival of the craft itself. This provides a useful comparison. Machines built from advanced materials require extraordinary protection simply to study the Sun from relatively close range. An unprotected human body would have no possibility of comparable endurance. There is also the question of where the Sun truly begins. Unlike a rocky planet with a sharp surface, the Sun transitions through layers of plasma whose density and temperature vary continuously outward. One cannot stand on it. One cannot descend onto it in any ordinary sense. Approaching the photosphere would mean entering an environment of extreme temperature and radiation, where matter behaves in plasma form and no solid contact is possible. Scientific descriptions can speak of temperature at different solar layers, but from the human point of view the important truth is simpler. There is no survivable boundary. There is only a continuous increase in hostility as distance to the Sun decreases. Visually, this region would be almost impossible for an exposed person to process for long. The Sun would dominate the field of view with unbearable brightness. Surrounding space would not feel dark in the ordinary way because the nearby star would flood the scene with direct radiant energy. Any nearby object, from spacecraft structure to stray dust, would reflect or absorb intense light. Shadows would remain sharp, but the distinction between lit and shaded would become part of a larger problem of thermal management rather than comfort. The eye itself would be injured by direct viewing. Vision would fail even before the full thermal and radiative environment completed its work. So the survival answer in the sunward limit is absolute in both principle and timing. An exposed human body remains a body in vacuum. So useful consciousness still lasts only seconds because there is no breathable atmosphere. Yet this region adds a second wave of destruction almost immediately through overwhelming solar radiation and extreme thermal loading. Closer still, the very structure of the Sun removes the idea of landing, standing, or enduring in any recognizable way. The inward journey through the solar system ends here because the Sun is not another environment to survive on for a moment longer or shorter than a planet. It is the source of the energy that shapes every other environment, and near that source, the human body has no natural defense at all. Survival does not narrow here. It disappears into light. The journey inward leaves behind a simple measure of survival and reveals a wider truth about the solar system. Human life is narrow in its environmental needs, but within that narrowness it is remarkably stable. When air, pressure, water, and moderate temperature remain in balance. Almost every world beyond Earth removes one or more of those conditions at once. Some remove all of them. The outer dark offers vacuum and cold silence. The giant planets offer deep atmospheres with the wrong chemistry and rising pressure. Mars offers land and sky, but only as a thin imitation of habitability. Venus shows how a rocky world can become unlivable through heat and atmospheric weight. Mercury, though solid and sunlit, remains exposed to space on both its bright side and its dark one. Near the Sun, the distinction between place and energy begins to fade. What changes from world to world is often the appearance of danger rather than its biological meaning. A black vacuum, A pale icy plain, a dusty red desert, a yellow furnace, and a cratered rock under fierce sunlight all seem different to the eye. To the body, however, the question remains steady. Can the lungs breathe? Can water remain stable in tissue? Can temperature stay within living range? Can radiation be kept low enough? Can pressure support the chemistry of life rather than destroy it? Only Earth answers yes to all of these in the open. That is why survival elsewhere depends not on toughness alone, but on carrying fragments of Earth outward. A suit, a habitat, a spacecraft, and a shielded shelter are all small acts of reconstruction. They do not make the planets gentle. They place a human world inside non-human ones. The solar system remains beautiful in every direction, but beauty and habitability are separate things. The body can admire many worlds. It can live naturally on only one.